But what is renormalization? Well, there's two kinds of infinities in physics. There's an infinitely small number. In general, a theory that comes up with an infinitely small number, the number can be discarded. It's not very important because it's a very, very small number. However, there's another thing that creeps up in physics, and when it does, it's called nasty infinities. And that is an infinitely large number. When an equation gives you an infinitely large number, you can't just say, I'm going to ignore that. So what is done usually, other than being said that the theory may be breaking down at that level, is that that number is renormalized. So usually what's used is a fundamental constant to cut the number. In this case, what was used was the Planck's distance. The Planck's distance is supposedly the smallest thing the universe does. You could think of it in really simple terms as the time or the distance it takes a photon to go across itself. It's the smallest wavelength the universe is supposed to be able to do. Do I think that the Planck's distance is the smallest thing the universe does? No. I think that the Planck's distance is a boundary condition that is a fundamental boundary in relationship to our experience. But I think that there's further definition, there's further structure below the Planck's distance. In any case, using the Planck's distance, which is 1.616 multiplied by 10 to the minus 33, extremely small, billions of times smaller than an atom, they renormalized the vacuum. What they did is they took a centimeter cube of space and they said, how many of these Planck's distances can we fit in, can we squeeze in into a centimeter cube of space? And if we do that, we'll have a finite number for the density of the vacuum. Basically, how much fluctuation of Planck's distances is there in a centimeter cube of space? So they stacked little Planck's distances full into a centimeter cube of space. Each one have a very specific mass, 10 to the minus 5 grams, and they added all up to get a fundamental density. The result was still extremely large. The result is 10 to the 93 grams per centimeter cube. That is an enormous number. You might have noticed in your bank account, every time you add a zero, it makes a big change. Imagine that you have 50-some zeros and you keep adding. At 93 zeros, right, you've got the density of the vacuum. Well, to give you an idea of how dense is that, imagine that you took all of the stars we see in the universe. There's billions of galaxies, they have billions of stars in them. Some of the stars are even much larger than our sun. And we took them all and we squished them all into a centimeter cube of space with like this huge trash compactor or something. You still wouldn't have the energy density of the vacuum because the universe is approximately 10 to the 55th gram. So 10 to the 55th gram squeezed into a centimeter cube of space is still some 39 orders of magnitude smaller than the structure of the vacuum, the density of the vacuum. So to think of empty space as empty is incorrect. Space is full. It's full of these fluctuations. It's full of this energy density that is actually, according to what I found, the source of all of reality.